A grocery store sells a bag of 3 oranges for $2.61. What is the cost of oranges in dollars per orange? So this is exactly the same stuff that we were seeing last time with two fractions that should be equivalent to each other. More on that today, but we can see that the two things that we're comparing here is dollars and oranges. In fact, in the question it says, what's the cost in oranges in dollars per orange? Remember, per indicates some kind of division. That's our fraction line. And the first label they've given us here is dollars. So that means it's going to be the label for our numerator. And then the second label, it's dollars divided by oranges, which tells us that oranges needs to be in the denominator. So since oranges needs to go in the denominator, it needs to be in the denominator for both. So I'm just setting up the fractions so I know where to put the numbers. And in the beginning here it says it's 3 oranges, so I know my first fraction will have 3 oranges here. And that's for $2.61, so 2.61. Now in the end, in the question, it says it's dollars per orange. That really means that we're looking for dollars per 1 orange, which, if we remember, right, hopefully, that's the unit rate. Right there, okay? How do we know it's a unit rate? Because our denominator, the oranges, is going to be 1. And that's what a unit rate is, where one of the two values is a 1. We just got to figure out how many dollars that is for every orange. So I would say, how do I make a 3-1 in the oranges, right? I take 3 divided by 3, that gives me 1 orange. So that means also I'll have to take the $2.61 and divide it by 3 as well. So I go to my calculator, 2.61, and I divide that by 3 to get 0.87. So that's 87 cents for every orange. And this tells us the cost in dollars per orange. So that's it. And again, this is what we would call the unit rate because we're looking at 1 orange. You could look at the unit rate for every $1, but that's not what we're looking for in this one. 3 objectives today. I can find the constant of proportionality in word problems and graphs. And also I know in tables, graphs, equations, and word problems are proportional. And then finally I can interpret proportional graphs. So take a minute and copy these down, please. So in our objectives, we see this word proportionality pop up quite a bit. Actually, we've already gone over the constant of proportionality, you'll see. And we've actually gone over proportionality. Just we're going to see it in different situations now. So proportions, all it is equivalent fractions. Just like we saw on the bell work, where we're looking at dollars per orange or dollars for 3 oranges. Those were equivalent fractions. They're equal fractions. So this is how they set up for us. We see these are 2 fraction lines with the equal sign. And yeah, sometimes these are labels in here, right? So it's possible that you may not have labels though, and that'd be fine. But again, we're looking at values that you'd put into these boxes like this. So they just have to be, whatever the fraction is, it has to be equal. So this takes us back, if you were to look at a situation. Let's say you're looking at a sandwich, okay? And it's a square sub because I suck at drawing. And you got some lettuce in there and some meat of some kind. Maybe that's ketchup and just lettuce, I don't know. In any case, you have a sandwich, and the truth is that you could take the sandwich if you wanted to, and you could cut it in half. Well, if you took 1 piece out of the 2 pieces, you'd have half the sandwich. But if for some reason you want to take this thing and continue splitting it up, it's possible that you could have the 2 pieces out of what was 4 pieces, and that would give you an equivalent amount. It's not like you get more sandwich, you just have more pieces, and they're smaller pieces, that's all. And if you wanted to continue dividing this up, not that I'm going to, because I've run out of space, you could say, maybe split it up into 6 pieces, so now you get 3 pieces out of 6, I don't know. Maybe you wanted instead 4 pieces out of 8 pieces. Okay, all of these are equivalent fractions. It's just shown in a different way. And so it is possible from time to time you may want 2 pieces out of 4 instead of 1 piece out of 2. Maybe it already came split up into 4 pieces, so that's what you get, half a sandwich. But you'd need 2 pieces to make that half sandwich. Now this, of course, these equivalencies continue forever and ever, and I have no desire to show them because there's so many, and I don't want to. In any case, it's important to understand that all these that we see here are equivalent. Now, on the other hand, one of these is the most simplified, and that would be 1 over 2. This one is considered the most simplified. Now, we've talked about simplification when we went over the fractions unit. We know it's most simplified because we can't divide the numerator and denominator by the same value without making decimals in this case. So that would make 1/2 the most simplified, okay? Now, of course, there's lots of different examples of equivalent fractions, but this should suffice in order to help us understand what we mean when we say proportional. Now, proportional, like we see here, it can be a comparison of equivalent fractions, that more than one comparison of 2 fractions. You can compare 3 fractions, you can compare 4 fractions, and so forth. It doesn't matter how many fractions we're comparing, as long as they are all equivalent. So for these examples, all we're going to do is look and see if these are proportional, or if they're proportional. So this tells us, just like we've seen with the equations, that we're actually going to put a question mark over the equal sign, and we're going to see if this is true or not. Because if it's false, then it's not proportional. If it is true, then it is proportional. So 5/6, we can actually look at these as just fractions. 5/6 right here, that can't be simplified. Can 35/48 be simplified? Well, 35 is divisible by 7 and 5, where 48 is not. So that would be considered the most simplified as well. And since we're looking at these, they're both the most simplified. But they are not equal. So this tells us that these 2 fractions are not proportional, okay? So they have to be equivalent to be proportional. Now, we could have just compared the decimals as well. So for this first one, you could have just said, well, what is 5 divided by 6? And then we can see what that decimal would be in our calculator. So in my calculator, I get 0.83 repeating. And then I can put 35 divided by 48 in my calculator as well and see what it gives me. So 35 divided by 48 in my calculator is 0.7291, and then the 6 is repeat. Well, clearly, again, these 2 decimals, 0.83 repeating, and this ugly piece of crap, they're not the same. So this is clearly not proportional. It really is that easy. Now, that's 2 different ways to do it. You can compare the fractions simplified, or you can compare the decimals. It's up to you. On the second one, and you could use the N over D button to simplify these, but I'm just going to divide these and see what we get. Okay, so for this first one, I'll do this first one here in red. So in my calculator, again, I'm just putting in negative 0.4 divided by 1.2, and I'm going to see what that gives me in the calculator. So negative 0.4 divided by 1.2, enter, and the calculator gives me negative 0.3. The 3's repeat. There's some bar notation, nice little review there. And then we got the second fraction here, 0.6. Again, I'm just going to the calculator, 0.6, and I'm using the divide button now. 0.6 divided by negative 1.8, and I'm just seeing what the calculator gives me here. Yeah, and I got the same exact decimal, negative 0.3 repeating. Okay, so since the decimals have the same value, the fractions are equal. So once again, that's just a little different. These 2 fractions are proportional. Okay. So again, we can compare the 2 that we had originally. And we can see here, this one, the 2 fractions were not equivalent, whether you simplified or used the decimals. These 2 here have the same decimals, and yeah, you could change these into whole numbers and simplify. If you did, you would have gotten the same fractions. These ones simplify into negative 1/3 if you were to do that. The constant of proportionality. We've already done constant of proportionality because constant of proportionality really is the unit rate. So as long as you know that you can find the unit rate, you can find the constant of proportionality. On the homework, it may ask for a constant of proportionality. You can put labels on a constant of proportionality, especially if it should be a rate. But if it doesn't give us labels, then it's okay to write a constant of proportionality as a simple value as well, okay? So, like we saw in the bell work, what was it, 83 cents per orange? The 83 cents per orange, that is the unit rate, therefore it is also the constant of proportionality. They are exactly the same thing. So we've gone over unit rates, and so I kind of feel comfortable saying that we can move forward with this constant of proportionality thing. We see a problem like this one. A 4 3/4 inch candle burns down in 19 hours. At what rate does the candle burn in inches per hour? So again, we're looking at two fractions because we are comparing inches and hours on this one. They should be equivalent, so we're looking at a proportional situation. And over here it says inches per hour, right? Really that's inches per 1 hour, which tells us we're looking at a unit rate, which then tells us that we're really looking at a constant of proportionality once we find this unit rate. There we go. All right. So, in the question part of this, they told us, remember per, that represents our division sign, but it starts with the inches, and then it divides the hours. So inches needs to be in our numerator here, inches. And if it's in that numerator, it needs to be in the other one as well. So there's inches. And then in the denominator, this is where we find our hours. Okay, so for the other denominator, also, we should find hours. And remember, I put the labels on first, because then we can just assign their corresponding numerical values next. And so reading this, 4 3/4 inch candle, so there's our first inches right there, 4 3/4. And you may say, well, that's not that's a mixed number and a fraction. That's okay. This is not going to be part of our final answer. Well, that's 4 3/4 inches in 19 hours, so 19 in our denominator. We know in the end we want 1 hour, so we're going to put a 1 there for our second fraction in the denominator. What we need to figure out is how many inches it will burn in hours, okay? So for me, I'm just going to type into my calculator 4 3/4. Remember, you can type in a mixed number like this. With the second function, push the second button there in the top left, and then the N over D button. You can type that in, and then I'm just going to divide that by the 19. Okay, whatever this gives me, that will be how many inches that would be in 1 hour. So 4 3/4, and I'm using the N over D button, divide by 19, enter, and it gives me this fraction. It's okay to have this fraction. It's 1/4 of an inch in 1 hour. Of course, you could have written this with a decimal as 0.25 inches per hour. It's really up to you, okay? And I'm not completely sure if the homework will accept the fraction, but I'm pretty sure we'll definitely accept the decimal. These are exactly the same. They're just shown with a fraction. One's a fraction, one's a decimal, and they are exactly the same value, which means if it were to ask for a constant of proportionality, you could say it's 1/4 of an inch in an hour, or 0.25 inches per hour. It's the same constant of proportionality. Again, you can represent a constant of proportionality as a fraction. You may represent it as a decimal as well. I hope that felt like nothing was new, except we did add a little bit of vocabulary there with the constant of proportionality business. All right, what about a table like this one? Well, it says the table below shows the cost of downloading songs from a website. Hey, that's great. Now, the thing we get to do on this one is we get to make the assumption that the table is already proportional, okay? So we're going to make that assumption, which tells us that each of the values should be equivalent. So for me, it says, what is the rate and cost per song? Well, we know per, that's division. So I'm going to be looking at division, and I'm going to be looking at all three sets of values here. It's cost, so I have cost per song. Okay, and that will that's going to repeat for all three of these. All right, so the first set that I see right here, $7.56 for 12 songs, right? $7.56. That's for, well, 12 songs. The next one shows $9.45 for 15 songs. And then the last set here, $11.97. That's for 19 songs. Now, we're assuming that the table is proportional, which means that all of these should be equivalent. But we can confirm this simply by dividing the values. So the first one that we see, $7.56 for 12 songs. So I take $7.56 divided by 12, and I just put this in the calculator to see what it gives me. 756 divided by 12, and I get 0.63. Now, having this 0.63 means that as I divide these other ones, I should also expect to see 0.63. Let's find out. 9.45 divided by 15 now. So in my calculator, 9.45 divided by 15, and it gives me 0.63, which is kind of what I expected. And then the last one, we'll do the same thing, 1197 divided by 19. And I'm going to use the decimal here, but when I put this in the calculator, it gives me 0.63. So we can see that all of these as decimals are exactly the same values. So that means we know it's first proportional. But also, this tells us that this value that we found, see this 0.63 that repeats? That tells us that we have also found the constant of proportionality as well. Okay, so it would be okay also to write this 0.63 as a rate, so we know it's dollars per song, which tells us really that we're looking at $0.63 for every one song. And that's actually what it asked for right here, right? Costs per song. Well, that was the unit rate. It was asking for a unit rate in costs, or dollars, per one song, which we just found. That's a $0.63, 63 cents per song. So in the future, when it asks us, and this was part of our objective, hey, is the table going to be proportional? You do have to check every single one of these values to see if they are equivalent. If they're not equivalent, or if you ever find that a set is not equivalent, then you can say right away that it is not proportional. So you don't have to necessarily check all of them. But if it is proportional, you would need to check all of them. So a little bit about graphs. Now, we've seen graphs as individual number lines, right? Like if I look at a horizontal number line, generally speaking, we'll put 0 right in the middle, and then we say each of these marks represents 1 unit, which means the 5th mark would be 5. And we know positives go to the right and negatives to the left, which means if I go 5 marks to the left, I would have -5. And for the most part, this is the kind of number line that we have seen. Horizontal is left to right, like this one. And we saw these, the example I'm thinking of is the inequality stuff. But it's possible to have a vertical number line like we used to have with our old thermometers, right? You'd say, well, 0 is right here in the middle, and the negative direction is down, and the positive direction is up. Now, of course, it would still say that each of these marks represents 1 unit, so 5 marks would be 5. If we go 5 up, and then 5 down here like this would be something like -5. Okay, so this is the way that the old thermometers were built. They put mercury in those suckers, so when I was a kid we used to break them, try to stab each other with them, which kind of explains how we are. But in any case, on this one, what we're going to be doing is we're going to be taking the graphs and we're going to be combining these two number lines into what we call a grid. Well, it's still a graph actually, but you can call it a grid. It's what we call the Cartesian coordinate system, not that I think you care, which means that we're really looking at a mapping. So it'd be like me taking this number line here and then fitting it onto this number line. I know it's not invisible, but it's kind of like combining these like this. And we end up with something that looks more like this. This is a map, and each of these lines you could say represents like a street, okay? So the x-axis, right there, that is the horizontal number line. like we saw on that last slide. And it's even labeled with an X right there, just to remind us, hey, we're looking at the X-axis right there. The Y-axis is the vertical number line, that's up and down. And just in case you ever forget that, they put a Y there just to remind you, this is the Y-axis. Okay? But you'll notice that these two lines come together right in the middle of both. That means that, remember, right, like we saw on that last slide, right in the middle for the X value, well, that would be 0 right there. And then right in the middle for the Y-axis, the vertical number line, that's also 0. Okay? What we get out of that is what we call the origin. This point right here, right in the middle, that's what we call the origin. Because it's where on the X number line, it's 0, but also on the Y number line, it's 0 as well. Okay? And in fact, from time to time, let's clean this up a little bit. From time to time, you'll see this point, and they'll even put like a little O right there. Actually, it's not a 0, which most students think, because it's a 0 for both X and Y number lines, but it's actually an O. It's the letter O for origin. Okay? So the origin, that's where the two number lines come together. And the origin is where well, do it like this. It's 0 on the X number line and 0 on the Y number line. Okay? Well, this brings us to what we call ordered pairs then. And there's more vocabulary with the graphs, but we really don't care, and hopefully we don't care for now. In any case, ordered pairs. Okay, an ordered pair, all it is it's a location on the map. Okay, so when we say, hey, look, find this ordered pair, we're looking for a specific location on the map, or you can call it a graph. Okay, so let's look at just some ordered pair. I'll just make one up right here. I'll do it in orange. Let's look at this ordered pair right here, okay? So ordered pairs come in this setup with parentheses around the ends. This tells us that we are looking at an ordered pair, and then we put a comma between these because you see here we have an X value, and then we have what we call a corresponding Y value. This is what we look at for the X and Y values that correspond to the X and Y number lines. So we're looking at this ordered pair. Where is it on the X number line, and where is it on the Y number line? Well, let's start the X number line, and it always is in this order. X's, then Y's. X's, then Y's. That's alphabetical, by the way, if you were wondering. Not that I think you were. But in any case, I can take this orange point that I put on the graph and see if I can follow this down onto my X number line right here, okay? Well, what is that value? There's two ways to find that value. You can count the lines. You can say, I'm going to count lines. It's starting at 0, 1, 2, 3, 4, 5, 6. So I see that that represents 6, or you could have counted the boxes, 1, 2, 3, 4, 5, 6 boxes, okay? It's really up to you. Most students, when we're getting used to this, count boxes, although later on, I find that students tend to count lines. It's really up to you. So in this ordered pair, I see the X value that's 6, so down here, I see that the X value is 6 for my X value. So I put 6 where my X value goes. Well, that's on the X number line. So I'm going to follow this. Again, it's kind of like a street. I'm going to follow this over to the Y number line right here. I just need to figure out that value too. So you can count lines. 1, 2, 3, 4, 5. So it's 5. Or you could have counted boxes. 1, 2, 3, 4, 5 boxes. So this tells us that the Y value that corresponds with that 6 is 5. So there's two ways to look at this. You can start with the ordered pair, a point on a graph like we did, and then find its location in numerical values as an ordered pair like this, or it's possible to start with an ordered pair and then be able to find that location on the graph. The reason why this will be important is because we're going to be having to notice ordered pairs on graphs specifically for unit rates. So this brings us to proportional graphs. What we saw on that last slide was just a point on a graph, right? But now we're looking at what we would consider lines, okay? So, for example, a line on a graph may look something like this one. Now we're going to pretend that Mr. Sal can draw really straight lines, and as unstraight as that is, we'll pretend like it is, okay? Now, we're looking at proportional graphs or proportional lines is really what that means. So we'll say, look, we're looking for proportional lines right here. Have a seat, please. So I'm looking for a proportional line, and this line, is it proportional? Well, if it's a proportional line, it has to be straight, and it has to go through the origin. This line, while it's supposed to be straight, it does not go through the origin. Remember that our origin is right in the middle of the graph right there, right? So right here, that would be our origin. So we know if the line doesn't go through this point, it's automatically not proportional. It's possible from time to time you may just have a point like this one. Well, it's not proportional because it's not even a line. Or you could have another point on a graph, you know, something like this, okay? Now, is it possible to have other lines on graphs? Sure, you can have a line like this one. And, well, that's the problem with this line right off the bat is it's not straight. So you know pretty quick, just from a visual check, that this is not proportional, right? And it is possible also to have, I guess, kind of like wavy lines like this one. So this one also, well, it's not proportional because, again, it's not straight. So all these examples that we're seeing right here, these are not proportional. And the only one that really seems like it would have a chance is a straight line. So, I guess it's kind of looks like a face right there. Let's clean the slate here and look again. So let's look at some examples that are proportional, all right? So let's look at, let's make this line right here. Okay, now you may say, well, Mr. Sal, you missed the origin. Fair enough. Let's start over because I suck at drawing straight lines. Let's try to make this one proportional. Missed again. Hey, that one's not too bad. This one is proportional. Yeah, but the line's not straight. I did my best. If you can draw straighter lines than I can, hooray for you, but I really suck at drawing straight lines. So here we go. Let's try another one that would be considered proportional here, okay? So it could be pretty steep as well. Again, let's pretend like that line's straight and goes through the origin. It doesn't have to be very steep, though. It could be pretty shallow like this one as well. All right? All three of these lines we would consider proportional because it's straight and it goes through the origin. As soon as we see anything that's curved or doesn't go through the origin, we know that it is no longer a proportional line, okay? So, unit rates in proportional graphs, they're going to be pretty easy to find. And the thing here is that we're gonna see lines that they should already start as proportional, okay? So this tells us that we'd have to look at straight lines, and they'd have to go through the origin. Okay. So as long as we can see right off the bat that the line is straight and goes through the origin, finding the unit rate really is not too bad. Because all we're doing is looking to find one on the x-axis. So if we look at one on the x-axis, that would be right there. And we're looking to where this line would, where this street, I guess, connects with wherever the line is. So let me just put kind of a random line on this. Well, maybe it'll be kind of random. I don't know. Something like this one right here, okay? So again, we're going to pretend like that goes exactly through the origin. And yet we have to pretend because sometimes Mr. Sal sucks, but whatever, okay? In any case, on this one, I'd say, look, it's always where the x value is 1, right? So when we're looking for the ordered pair, we're just looking for where the line goes through, or where the line is 1 on the x value. So this means I'm just going to follow this line up until I meet that purple line right there. See this? Now we'll pretend like that went right through that value right there, which appears to be a y value that is 2. So for example, on this particular line that we've drawn, the ordered pair for the unit rate is 1, 2. Now right here you see that this is a general situation for us, so but it's important that right here, just that we understand the x value is always 1. I know it says that, but I can't emphasize that enough because it's so easy to find, as long as you can find where the x value is 1 on the line, okay? So all you have to do is find where that corresponding y value is. Will it always be positive y value? No. If the line went down here somewhere, then it could be a negative value too. Okay, so something like this when it says find the unit rate for the graph and then we'll interpret the ordered pair for r. Fair enough. In fact, we'll interpret both ordered pairs because we're going to find the unit rate on the graph, right? So let's look here a little bit closer. In fact, even a little bit closer. Yeah, that's good. So for the unit rate, remember that the unit rate has to have an x value that is 1, right? Well, I can find the x value that's 1 right here. And I just follow this line up until I meet the line, which is actually at the ordered pair for s. So to find its corresponding y value, just follow this over, and I see that its corresponding y value is 10 right there, okay? So this would be my ordered pair for the unit rate. So yeah, we found the ordered pair for the unit rate. But can we interpret that? Yes, we can. We can see here that the x value is 1. And then its corresponding y value is 10. Now, it didn't ask us to interpret this, but I'm still going to because what the heck. And on this one, all I've got to do, since the axes are labeled, the x-axis is horizontal, y-axis is vertical, it's labeled. So I can just label these numbers. I see I'm looking for an x value, so I'm looking for a label on the x-axis. Boxed lunch is ordered, okay. So right there for my 1, that's 1 box lunch ordered. And then for my 10, I can see up there that it's the y-axis label is total cost right there, so I can put that in there as cost. In fact, maybe I don't even need the text box there. It's just, I'm going to put it in dollars, okay? Now to take this just a little bit further, I'm going to interpret this because we can, okay? It's saying that it's $10 per 1, I'll just say box lunch. Okay, or you could say every box lunch costs $10. Doesn't really matter. It's the same exact interpretation. But it does ask for interpretation of the ordered pair for R. So let's find the actual ordered pair for R right here. Okay, so again, I'm going to follow my x value down. And I see that that brings me to the x value that's 4. So my x value is 4. And I can follow this street or line over to the corresponding y value, which is 40. So I got 440. So let's go ahead and interpret that though, because that's what it asked us to do. So again, let's look at our x value, which is 4, and then its corresponding y value, which is 40. Okay, well, we already know the labels for these. It's 4, we'll say that's boxed lunches, for $40, okay? So I'm going to interpret this 2 different ways. We can say it's $40 for 4 boxed lunches, or if you wanted to, you could say that it's 4 boxed lunches for $40. Same thing. Now, is that a unit rate? It is not, but you can see if you were to take the 40 and divide it by 4, you'd get the same exact value as 10 divided by 1. Which again, just from the ordered pairs, we can tell if a situation is proportional, just like we saw with the graph, and also in a word problem, which is part of our objective today. So the constant of proportionality in graphs, it's just the unit rate, remember? And since we already know how to find the unit rate in a graph, all we really need to understand is that when we look at the division, it's always that you're going to be taking the y value and dividing it by the corresponding x value, and you'll have your constant of proportionality, okay? Y values divided by x values, and so the nice thing is, if we have, let's put a straight line on this one. I don't know, something like this one, right here. Now, yeah, you could say, well, look, I'm just going to look for where the x value is 1. That'd be this line, and it goes through 1, 1. That's fine. But if you have another point, let's say this one right here, this ordered pair, so it looks like it goes to this line right here. That's 1, 2, 3, 4, 5, 6, 7, 8. So the x value is 8, and its corresponding y value would be here. And it's a 1, 2, 3, 4, 5, 6, 7. Oh, it's 8 as well. That should be different, but in any case, you take the y value, which is 8, and the x value, which is 8, and you can divide those. It just has to be in that specific order. Y values divided by x values, and you will have your constant of proportionality. So, proportions in tables, which we've seen. Remember, just like we saw in that last example with the table, we have to take all the corresponding values in a table, and then it's just, since we're looking perhaps for a constant of proportionality, you have to take the y values divided by the x values, okay? So in a table, and this one is more like a t-table like this, you're going to see always that it will be the x value first on the left, and the y values should always be on the right. The reason why this is the case is because it creates for us ordered pairs in the table, okay? So, right here it says divide all the x values by the y values. Remember, though, because we are looking for the constant of proportionality, you need to take the y values and divide them by their corresponding x values, whatever they are. Now, if all the answers are the same, whether you use decimals or fractions, doesn't matter. But if they're all the same, then we know that the table represents a proportional situation. If at any time we find that the values are not the same, then we would say it's not proportional. So, of course, to find a constant of proportionality, it has to be proportional first, just like we saw on the example with the table earlier. But if we find that it's not proportional, there's no need to find a constant of proportionality because it's not proportional. So let's look at this example right here. Determine if the table is proportional. Fair enough. Let's do that. Okay. So remember, in each of our fractions, we're going to be taking the y value and dividing it by the x value. If it is proportional, we'll say what the constant proportionality is to. Okay, so on this example right here, now we got x's and then you have y's, but you take the y value, which in this case is 2, and divide it by the x value, which is 3. And as a fraction, this would be 0.6 repeating. All right, that's pretty good. Let's try the next set. So again, as a fraction, I have a y value that's 8 and an x value that's 12. And yeah, you could say, well, look, 8 and 12 are divisible by 4. That would give us 2/3. They're equivalent. Or you could use the fraction, which is 0.6 repeating. And these are the same. Now, is this enough to say that the table is proportional? It is not, because we now have to check this last set as a fraction. The y value is 10, and the x value is 14. Okay? Now, just real quick, just so we remember, as a fraction, this simplifies into 5/7, which is definitely not 2/3 or 8/12, which means that right here, just from the fractional part of that, I can see that it is not going to be proportional. But just to confirm it, let's look at the decimal, 0.714 and some other garbage. It's pretty ugly decimal. In any case, I can see right here, these fractions are not equivalent. They're not equivalent or equal. So this situation, so this table is not proportional. There we go. Now, again, if it were proportional, I would find the constant of proportionality, but it's not, so I don't have to worry about it. All right, you guys take a minute, see if you can figure out if this table is proportional or not. Then we'll go over it together. Okay, 1 minute. All right, so remember in our ratios or rates here, I'm comparing y values to x values. So it's y's divided by x's for me. And on this first one, as a fraction, the y value is 1, the x value is 5, and that as a fraction cannot be simplified, but it does give us the decimal 0.2. Now, remember, one fraction is never enough to determine if a table is proportional. We have to check all the other values as well. So on this one, the x value is 2, sorry, the y value is 2, and the x value is 10. And yeah, this actually would have simplified in 1/5 anyways, but as a decimal, you'll still get 0.2, okay? So these two values are equivalent, which means that between the two, they're proportional, but is the rest of the table proportional? That's what we need to find out. So for my next fraction, though, the y value is 10, and the x value is 15. Now, if you were to simplify this one, though, the problem here is that you get 2/3, which is not going to be 0.2, that's 0.6 repeating. Very different value. So right here, just from what we see, is that the fractions, or I guess I should say, not all, and that's the important part, all of the fractions are equal. So this table is not proportional, okay? And yeah, you could have said, well, the fractions are not equivalent as well. And we do not see a need to test this last ordered pair, because right here between the first three, we can see that they're not proportional. So there's no need to check that one. Right here, we're just gonna say it's not proportional. Now, since it's not proportional, there is no constant of proportionality. Again, if it were proportional, then we'd be able to find that, just like we did on the first table example today. Well, this one's not, so there's no need to do that. Last up here, we got Jackie has just gotten a new job. The relationship between the number of hours she works, X, and her total earnings, Y, is represented by the graph drawn in the XY plane. The problem with this is that it does not give us a graph drawn in the XY plane, which is really just kind of like that mapping that we saw, right, where the two number lines come together. And even on the assignment, it'll be worded this way, but they're not going to give you the graph. The important part here is that we see that the X's represents number of hours that Jackie works, whereas the Y represents her total earnings, which we'll just show in dollars, okay? So we have both values. I got an X value here. That is 6. And a corresponding Y value. That is 210, okay? So what do these represent? Well, it says up here that X is number of hours she works. So if she works for 6 hours, we see that the Y value represents total earnings in dollars. Well, that means she would make $210. Now that would be good enough, but I'm going to be a little bit more specific on this by writing some sentences. So just the way that I have these orders, it means if Jackie works for 6 hours, she will make $210. Or if for some reason you wanted to rewrite this, you could say to make $210, Jackie will have to work 6 hours, okay? Both those say exactly the same thing, they're just saying it in a different order, that's all. And of course, there's other ways to represent those, but hopefully that's good enough for now. So full circle, this brings us back to the objective. We saw examples where you had to find the constant of proportionality in the word problems, like we did in the bell work, and also in graphs. And now hopefully we can know in tables, graphs. We didn't see equations, and that's okay. You could pretty much cross that out if you wanted to, but we'll see equations later. But we also need to know when tables, graphs, and word problems are proportional. And then also when they've given us a proportional graph, we should be able to interpret the ordered pairs on that graph.